have a more particle physics perspective of what dark matter is. So look at the clock, okay?
Okay. Do you hear me? No. So do you hear me? Okay. So, yeah. So thank you, organizers, for this opportunity. I'm a postdoc at Carleton University, and I did undergrad and master very close to here at University of Paraíba. So I'm very happy to be here today. So this is the outline of my talk. I will first, in the first half of the talk, I will introduce the so-called freezing production of dark matter, and also I will tell when it's important to consider it along with a reheating period, and I will try to explain what is it in some detail. And in the half of the talk, I will discuss two models in which the freezing production is actually expected to happen, and especially during a reheating period, as I'm going to show. So, and then I conclude. So in this introduction, I will explain, here in this cartoon, there is I represent the thermal production of dark matter at first. So in this, these yellow dots are the visible particles described by the standard model. These purple dots are dark matter particles, and they evolve in an expanding universe. So if the interactions between dark matter and standard model particles are strong enough, we start in a thermal equilibrium situation in which the total numbers of both species do not change because they are being produced and annihilated at the same rates. And then dark matter starts to be very heavy, has to be produced, and then the total number of dark matter freezes out of equilibrium, and we have the final relic density established. That is today 27% of the cosmic energy. So this is the freeze-out mechanism, and these dark matter particles with this origin are the WIMPs, and the famous WIMPs. So another possibility is that the visible sector started producing dark matter, but before this thermal equilibrium situation could happened, the production of dark matter, the production rate of dark matter start to vanish, and then we have the same final relic density that we see today. And for this to be possible, this is the freezing production, this freezing mechanism, and for this to be possible, the couplings between both sectors needs to be weak enough, so they are the feebly interacting massive particles, the FIM, to avoid the thermalization at the beginning. So let me discuss a bit the relationship between the genesis of dark matter and the phenomenology. If we have some set of, if dark matter has some set of couplings to a standard model, we, in the early stages, as I showed before, we can have a kinetic equilibrium between the dark and visible sectors via number conserving interactions. And also we could have a chemical equilibrium via number violating interactions such as annihilations, decays, or this 4 to 2 processes. And on the other hand, we can probe these particles at direct, indirect, and colliders. And the way these couplings are related to each other is, of course, dependent. But so here I just distinguish to be more general. And this is just to remember the results from direct detection of dark matter. We see that a lot of models of WIMPs are already excluded. Of course, it's not dead, but it's already excluded. And that these colored lines are future prospect for future experiments of direct detection. And we see that they will be able to probe the FIMP scenario in the future. So the point I want to make here is that the couplings probed by direct detection experiments, which can be related to the couplings leading to the kinetic equilibrium at the beginning, needs to be smaller and smaller as to evade these bounds. So we might think about some theoretical floor for the couplings of a thermal production, because at some point we would not have equilibrium anymore to be able to have equilibrium at the beginning. So I will try to make this more explicit here. Here we see the evolution of the co-moving amount of dark matter for the WIMPs. So since we have a thermal equilibrium at the beginning, the final relic density is usually it does not depend on the initial conditions. So the final relic density will depend only on masses and couplings, and then the good thing is that for masses and couplings in the weak scale we have the good relic density today, and also we can probe these couplings already. But the point is that it's straightforward to see that stronger bounds from direct detection make the WIMPs annihilate less because the couplings need to be smaller and smaller. So we end up easily with an produced dark matter. Okay, so in the case of the freezing, this tension is not present because we do not annihilation rates. So the freezing happens. Here I show the evolution of the relic density as a function of the inverse of temperature normalized to some mass. And we see that the relic density levels of the freezing happens once the production rates start to vanish. So since we have an out of equilibrium production, this can depend on the initial conditions. So I will explain in each way. But if we have contact interactions of this kind, for instance, we see that the freezing happens at the only scale available, which is the mass of dark matter. So in this case, the freezing is also said in as well as this freeze out, because the final relic density will depend only on masses and couplings. And in this case, we are left with the only possibility to have very small couplings, and it's more difficult to probe, right? But also, if we have, if the freezing happens through the exchange of some heavy mediator, we can have larger dimensionless couplings, and the freezing is usually happening in the early stages of the universe and will depend easily on the initial conditions set by inflation, for instance. And in this case, the couplings that would lead to a thermal equilibrium in the beginning must be very small. So it embeds that this agrees with the constraints that we have. If we lower the couplings, the FIMPs become underproduced. So this might be interesting for models with a complex dark sector. Okay, so of course the freezing is not the only way to avoid this tension between the direct detection and the thermal production. Here I list some possibilities of avoiding this tension, and of course I'm sure that you can give a lot of other suggestions for this list. So we can make the bounds weaker by invoking models with pseudoscalar couplings, by separating the couplings that led to the freeze out with the couplings that are probed by direct detections. So for instance, if the freeze out happens through annihilation into bosons, for instance, co-annihilations also like by invoking another particles involved in the freeze out process. And also, since the coupling conditions is essentially a comparison between the interaction rate and the Hubble expansion rate, by changing the Hubble expansion rate, we can change the predictions of the model. So we can this is also interesting for freezing models, because if you make Hubble rate larger, it's easier to have decoupling. So we can raise the couplings, the strength of the couplings. So this is also interesting. And also we can change the assumptions regarding the dark matter interactions. For instance, dark matter can be in a different thermal bath with a different temperature, and then we have dark freeze. Right, so we have a dark freeze out, and couplings leading to the dark freeze out are not probed by direct detection. So we have quite a freedom. And also we can have non-thermal production from a completely decoupled sector. For instance, if the dark matter is produced from the inflaton directly. And also this is different from the freezing, because in the freezing is the visible sector is producing the FIMPs, the dark matter. In this case, it's the standard model sector. So now I will focus on this freezing production. And before showing my results, I will explain the main physics at play in these results, because we are invoking heavy particles, And then these heavy particles can be, but I will show. So this is the landscape of the dark matter genesis. We have, in order for the dark matter to dominate the energy density of the universe in the matter era, they need to be produced not much later than the Big Bang nucleosynthesis. So So we do not know what happens. We don't have, as we saw yesterday, we don't have data from the universe above the BBN nucleosynthesis around the MeV scale. But since the BBN is well accommodated in the standard model, it's reasonable to assume that early in the universe at 100 MeV, we have the quarks and gluons were free, and even earlier, we have the electroweak symmetry breaking, and the weakened electromagnetic interactions were unified. So, and many open problems of the standard model, for instance, the generation of neutrino masses, the matter and antimatter asymmetry, can be solved by invoking new physics happening from hundreds of GeV to the Planck scale at 10 to the 19 GeV. And so we have this, in this landscape, we have these structural extensions of the standard model. For instance, unification of electroweak and strong interactions that can happen at intermediate, can break at intermediate scales of 10 to the 10, 10 to the 16 GeV. And finally, the seeds of structure formation of the genesis of matter could be explained in these inflationary theories, in which in a field called inflaton make the universe expand exponentially and then decays into standard model particles, and would be the start of the radiation era. And we don't know, it will end at some scale called the reheating temperature, and we don't know what is its scale. Here I show the general orders of magnitudes of ignorance that we have about that, which can be constrained by the CMB, and I left with this reference here. So we see that it's completely possible that some reheating period happened. And in the models that I'm going to show here, we are inspired by structural extensions of the standard model, and we will consider the freezing during this inflationary reheating. Okay, so in order to understand how a reheating period could affect the dark matter relic density, I'm going to show the equation behind the drawing in the introduction, and it's the Boltzmann field equation, and it basically tells us that the total number of dark matter can change in an expanding volume of the universe. This is the scale factor, if there is some global production or annihilation of dark matter. So this is encoded in the production rate, okay, in the interaction rate. So the way the scale factor changes with temperature depends on the content, the energy density of the universe, and this is encoded in the Hubble rate. So if we have a thermal bath, we can describe this, the evolution of dark matter in terms of the temperature instead of the time, and a way of defining temperature is through the total entropy. And if the total entropy is conserved, the evolution is given in terms of the yield of dark matter, which is a number density normalized to the total entropy. So this quantity here can only possibly change if we have some departure from equilibrium. And this is the equation that we usually solve for the relic density of dark matter for the evolution. But if the entropy, if the entropy is produced in some period of time, we can define a ratio between the total entropy after and before this period of production. And then we can easily see that this delta will be a dilution factor, because if this period of entropy production happens after the relic density of dark matter has established, we can easily see that the yield after will be smaller than the yield before. Okay, so possible to produce entropy is by the out-of-equilibrium decay of some field that here I call some unstable field, which I call phi. it decays into radiation. Okay, while this is happening, we have reduction. The total entropy, the total energy density changes. So, and it's interesting to see that this delta that dilutes the dark matter relic density depends exclusively on the physics of this unstable field. Okay, so if it's long-lived, it will produce a large amount of entropy. Okay, in this case, the evolution of dark matter needs to be solved along with the evolution of this unstable field and the decay products. So we need to solve these Boltzmann equations. And here I show the solution for the radiation and the inflaton, in this case, this unstable field, as a function of the scale factor normalized to this inflaton mass. And we see that we have, while the inflaton is decaying, it's producing entropy and then radiation till the moment that we have this reheating, this so-defined reheating moment, where the total relic density of radiation is established. So we enter in the radiation era, the start of the radiation era in the universe. And then the entropies start to be conserved, okay, as we see here. So we can see that this process is not instantaneous. It is finite. It has a finite duration, of course. And in the freezing, dark matter is produced from radiation, from the thermal bath. So the production of dark matter can happen here, while we have the production of radiation. So here I show how the temperature of the thermal bath is changing while this is happening. And we see that we have a maximal temperature in the thermal bath, which can be much larger than the reheating temperature. It depends basically on the physics of this field, which is decaying, which is in this case the inflaton. And we see that the universe, while we have this non-isentropic expansion, cools down slower. Okay, so the temperature goes with the scale factor to the minus 3/8. So the reheating in the case is it cools down slower. And here in this green curve, Hubble rate. So we see that we go from an epoch in which the inflaton dominates the Hubble expansion, and until the epoch close to the reheating scale, that the radiation starts dominating the cosmic expansion, isentropic cosmic expansion. So the relic density of dark matter has in principle these two contributions from the production during reheating and the production during radiation. And I leave you with this nice paper where they consider how this can change the relic density of WIMPs. Okay, if the WIMP mass is above reheating scale, which is possible, as we saw, like it can be MeV scale, tens of MeV scale. If the WIMP mass is larger, if we have a low reheat temperature, so this can affect the predictions of WIMP. And this is one of the first papers. FIMPs were considered. They also considered FIMPs. So if you have in your spectrum of beyond standard model spectrum, if you have some particle that decouple from the thermal bath while it's ultra-relativistic, the same physics would happen. Okay, because if it decouples ultra-relativistic, once it becomes non-relativistic, then the energy density of this field would start to dominate with respect to the energy density of radiation. So we would have an early matter era, and if this particle of your spectrum is long-lived, this matter era would end up with entropy production, okay, with a secondary reheating, for instance. And we actually don't know how many of these events happen in the early universe, okay, so this is quite general, and it's interesting to see when this could be important. How can this affect the relic density? So this is how the temperature also evolves while this is happening. We see that everything depends with the temperature dependency of temperature and scale factor relation changes if we have the entropy production. And this is why in the early matter era, in the matter era, depends on temperature like 3/2. And if we have entropy production, it's T to the 4. So it's more suppressed. So how can we when this can be important, like when the freezing happens? So the squared amplitudes of your model can give the answer, because at some approximations we can see that if the production rate depends on some power law of temperature, we can see that the contribution of production during radiation has this form here, and it's easy to see that if the power of the temperature is smaller than 5, the final relic density will depend only on the lowest scale available of the problem, which is usually the thin mass. And if it's not, if it's larger than 5, then everything will depend on the reheating temperature, which is the highest scale of the radiation. And the same analysis holds for the production during reheating, and this power is 12. Okay, so this is the physics behind the models that I'm going to show, and I'm going to show the first model, the spin-1 portal. So extended by some extra U1 symmetry is interesting, and it's a phenomenological rich option. And if the Z prime, the standard model fermions are charged under the Z prime, we have we can have a easy portal for WIMPs. And if for Z prime in the mass of TV scale, we have good relic density for WIMPs in the GV to TV range. And the point is that the colliders constrain the Z prime, and if the bounds on Z prime becomes stronger and stronger, it means that it's heavier or interacts much feebly, and this makes the portal to WIMPs inviable. Another possibility is that the fermions of the model are neutral under the Z prime, and in this case, if we have heavy fermions charged under both carrying standard and dark symmetries, quantum numbers, we can have a portal, an effective portal between the standard and dark sectors. That I'm going to show here. In accounting for mass of the Z of these heavy fermions, we usually invoke heavy scalars that can have some real and axial components and have at a high temperature. And so we have this kind of diagrams here. And at temperatures below the mass of these fermions, we have these effective couplings like a Higgs-like operator and the psi-queen operator. And we see that these fermions can be under the hypercharged bosons, for instance, in this example here. So but if these fermions are charged under a U1 prime, we have this kind of interactions that will give generalized Chern-Simons couplings, the so-called Simon couplings, which will be 3 gauge bosons couplings. And we see that it will vanish if the fermions are non-chiral under the Z prime, for instance. And the interesting thing here is that this Z prime acquires masses through the Schuckerberg mechanism, provided that this is heavier. We can have the gauge variations of the axion part and the generalized Chern-Simons parts together. So the 3 is anomaly free, provided that this I have to run a bit. So this is our minimal extension of the standard model. We have this local U prime with gauge boson Z prime. Our dark matter is can be a fermion, an abelian, and a non-abelian vector. And we have we invoke the presence of heavy fermions, and these are our freezing diagrams, processes. So we have a non-resonant exchange of Z primes, and this is our effective Lagrangian. So we have this new physics scale here, couplings to dark matter and the masses as free parameters. So since, as I said, here from the amplitude squared, the squared amplitudes, we can see, we can understand how it will be produced. So here are the limiting case of the squared amplitude. So we see that it features a non-resonant exchange. And also we have, as we have more and more effective currents, we have larger and larger temperature dependencies. And why it's important? Because if we have a large temperature dependency, the production during reheating will be important, because then it can overcome the dilution. So here is the production rates, where we can see the different temperature dependencies. And the higher the temperature, the more dark matter is produced. And also we see that very heavy dark matter cannot be produced anymore because we have the boson suppression. So here is how the relic density evolves in this case for our 3 dark matter candidates as a function of the inverse of temperature, essentially the time. So in our case, as expected from our analysis of temperature dependency, it will happen at most at the reheating temperature. So before the radiation era, we have the production of dark matter. And the stronger the temperature dependency, the production happens earlier and earlier, okay? But of course, we want to have the good relic density. And these are the contours in our parameter space in agreement with the relic density constraints from Planck. So this is the dark matter mass and the new physics scale. And we see that we can have a good relic density for Z prime mass and new physics scale at intermediate scales. So we don't need to have super heavy dark matter. Dark matter can be of, for the vector case especially, very light. And we have order 1 couplings. This, for the case of a billion, is small because it's given by in terms of the charges and gauge couplings of the fermions. So we see that it's quite a natural realization, okay? And we can explain the good redundancy. So in the second portal that I'm going to consider is inspired in unified descriptions between the weak, electroweak and strong, and also gravity interactions. So as we know, the electromagnetism is mediated by massless spin-1 fields, the photons, and the source are vector currents, okay? So analogously, since everything that have energy gravitates, the stress energy tensor would be the source of a quantum gravity interaction. And then that's why the gravitons, the massless spin-2 fields are expected to mediate gravity, okay? And in this way, all the standard model fields would be very weakly coupled to gravitons, an interaction that's suppressed by Planck scale. And then, since all the evidence for dark matter comes from the gravitational interaction, it's interesting to see whether these feeble couplings of the standard model and dark matter to spin-2 fields is enough to produce the Friesen. Okay, so here we consider a graviton, a mass spin-2, which is present in extensions of this kind, and there is considered scalar fermion vector. So the standard model would be able to produce dark matter through the exchange of massless and massless fields. And this for effective Lagrangian, everything that interacts is universally Planck suppressed, while interactions with a spin-2 is much less suppressed by some lambda, by scale of new physics, which is smaller than the Planck scale. So here is our production rates as a function of the inverse of temperature. We see that because, okay, since even though the stress energy tensors are different for scalars, fermions, and vectors, at the limiting phase of light dark matter, they behave essentially in the same way. And we see that we have 4 regimes depending on the relation between the mass of the mediator and the temperature. So if we have here left with this with the production rates for us to understand how is the production rates. So if the mass of the mediator is much lighter than the temperature, it is essentially as a massless particle, and we have the light regime. The relic is the production rate is has its temperature dependence, T to the 8, and depends only on lambda. when the temperature of the universe is enough to produce this spin-2 shell, we have this pole region. We don't have a temperature power law, but we have this function. If it's heavy, the production rate is suppressed by the mass of this heavy scalar, of this heavy mediator, and the exchange of a much heavier spin-2 becomes at some point much more suppressed than the Planck suppressed interaction, and we have the graphton dominating the freezing. So here is the evolution of the relic density for our three candidates, behaving essentially the same way. And we see that the freezing happens either close to the scale or the mass of this mediator. Okay, and here is the agreement with the Planck constraints. We see it in the plane of the mass of the mediator and the reheating temperature. So since in all the cases the freezing would depend on the temperatures on the reheating temperature, let us focus on this line here. So if the mass of the mediator is much below the mass of the scale of reheating, we have the light regime. The relic density is fixed only by the reheated temperature. This is for true values of dark matter mass. Sorry, I didn't mention. For 1 GeV dark matter. So if the mass of the mediator is close to the reheating scale, we have a huge enhancement in the production rate, and then the reheating temperature needs to be sharply lowered as to not overproduce the films. Here we have the heavy regime and also the graphton regime when the mediator is much heavier. Of course, we can break this. We need to break this parameter space here to not be so heavy. So we see that we also have good relic density for reasonable values of reheating and the mass of this particle, this heavy spin-2 field in intermediate scales. So I just want to emphasize the importance of considering a finite duration of the freezing or the reheating period if the freezing happens through the exchange of heavy mediator. Here I show the ratio between an exact computation of the relic density, taking into account the set of coupled boson equations, to the relic density computed, just assuming that dark matter was produced after the start of radiation era. So we see that as a function of the spin-2 mediator. And if this spin-2 mediator happens to be in the scale of heating period, we have a huge underestimation of the relic density with respect to this instantaneous reheating approximation. So let me conclude. We see that the direct detection bounds if they push the couplings between dark matter and incident model to lower and lower values, we might have a tension with the thermalization condition, because the freeze out would easily lead to an overproduced dark matter. The freezing is an interesting alternative to that, and it's easily embedded in structural extensions of the standard model. We have seen, and also we don't know the scale of reheating. And it's important to consider carefully the finite duration if we have these heavy mediators living around, okay? Because we don't know the scale. So I'll just briefly give in some perspectives. We can really expect new developments in direct detection, and even recently, the FIMP mechanism was started to be probed by direct detection. Lux is already excluding some part of the parameter space in the case of light mediators. So if the T-channel exchange of light particles can enhance the cross-section enough as to overcome the small couplings needed for this is the mixing, okay? And we also new bounds in the future. And I will finish this by mentioning Methuselah, which is a detector proposed to be built in the top of above Atlas or CMS, and it will be maybe the first or only discovery opportunity for a lot of scenarios that these motivations of as we mentioned here, like for instance axinos, the FIMP, it can probe FIMPs. Extra gauge bosons, mechanism for mass of neutrinos, and unification of and the generation of tree between matter and matter. So we can have an interesting future ahead. Thank you.
Further, any questions? Sorry.
Hi, great talk, thanks. I didn't understand quite how does the Z prime connect back to the standard model?
In here?